A $5 mechanical valve can stop a house flood in seconds, yet most homes are built without it. Every year, water damage quietly causes tens of billions in losses, not from hurricanes, not from disasters, from small internal failures, supply lines, fittings, connections under constant pressure. When they break, they don't leak, they release. Pressurized water flows uninterrupted, often for hours until someone notices, or until the structure itself starts to give way. Flooring absorbs it, drywall traps it. Electrical systems begin to fail behind closed surfaces. By the time it's visible, the damage is already extensive. 5 figures is common, sometimes more. And what makes this harder to dismiss is that this risk isn't new. Basic mechanical shutoff concepts, pressure-triggered, flow-limited, have existed for decades in industrial systems, nay, irrigation controls, even early plumbing safety designs. The mechanism is simple, the physics is predictable, the outcome is preventable, at least in certain types of failures. And yet, in residential construction, this layer of protection is rarely standard. Welcome to Trust No Instinct. If questioning incentives matters to you, subscribing keeps this thinking alive. So the question isn't whether the solution exists, it's why it isn't built in. In environments where liability was measured in lawsuits, shutdowns, or cascading system failure, water was never treated as harmless. It was treated as a force that had to be controlled, especially when something broke. Industrial systems understood this early. In facilities where downtime could cost thousands or more per hour, a ruptured line wasn't just damage. It was exposure, financial, operational, legal. So they didn't design around the hope that failure wouldn't happen. They designed around the moment it did. Mechanical shutoff valves, flow-limiting devices, pressure-triggered controls, simple systems, immediate response, no software, no delay. Because the principle was already clear. Failure is inevitable. Uncontrolled duration is optional. If a system breaks and stops itself, the damage stays contained. If it doesn't, it escalates. Fast. That same logic appeared in other controlled systems. Large-scale irrigation, process piping, environments where continuous flow meant continuous loss. The goal wasn't perfection, it was interruption. Stop the flow, limit the damage, control the outcome. Even within plumbing engineering frameworks, this wasn't unfamiliar. As the idea of limiting uncontrolled discharge existed. It was documented, technically understood, mechanically achievable. So, the capability was never the issue. It was the context. Because residential plumbing evolved under a different set of pressures, not failure containment, but reliability under normal use. The objective wasn't to manage rupture. It was to prevent rupture from happening at all. Stronger materials, better fittings, standardized installation, code compliance built around expected conditions. And to be fair, this approach works. Most homes never experience catastrophic failure. Most systems hold. But that success carries an assumption. Failure is rare, so planning for failure becomes optional. And that's where the split becomes structural. In high-consequence systems, failure is part of the design model. Yes, in residential systems, it's treated as an exception, not impossible, just unlikely. And once something becomes unlikely, it stops being prioritized. If it's not required by code, it's not specified. If it's not specified, it's not installed. If it's not installed, it's not expected. And if it's not expected, it disappears, quietly, not removed, not rejected, just absent from the baseline. Builders follow code. Inspectors verify compliance. Homeowners inherit what's considered standard. And standard doesn't mean optimized. It means sufficient under normal conditions until something breaks. And when it does, it doesn't degrade slowly. It doesn't signal. It doesn't give you time to react. It opens and it keeps going. That's when a decision made years earlier, something small, something optional, almost something never required, suddenly determines the scale of the outcome, contained or catastrophic. And this is where the shift becomes harder to ignore, because the protective logic existed first. The physics never changed. The risk was always understood. What changed was what the system chose to assume. And once you see that, You're no longer looking at a missing component. You're looking at a difference in priorities. Part 3, Scientific Connection, approximately 410 words. Once you strip away the framing, the mechanism itself is almost unsettlingly simple. Residential water systems operate under constant pressure. Every pipe, every fitting, every connection is part of a closed system designed to deliver water instantly the moment a valve opens. But that same pressure creates a hidden condition. If the system opens unintentionally, it doesn't slow down, it accelerates. When a supply line ruptures, this isn't a leak in the traditional sense. It becomes an open flow event. Water moves from a controlled pathway into unrestricted space, driven continuously by pressure from the main line. And unlike gravity-fed systems, it doesn't taper off, it sustains. This is why water damage escalates so quickly, not because of volume alone, but because of duration under pressure. And this is where the valve changes everything. A mechanical shutoff valve doesn't detect water the way a smart sensor does. It doesn't analyze data. It doesn't wait for confirmation. It reacts to physics. Most designs operate on one of two principles: a sudden drop in downstream pressure, or an abnormal increase in flow rate. Both are signatures of failure. Inside the valve, a spring-loaded mechanism or diaphragm is calibrated to respond when those thresholds are crossed. The moment the system behaves outside its expected range, it closes. Not gradually, not conditionally, immediately. And that timing is what matters. Because the difference between a controlled incident and a catastrophic one often isn't whether a pipe breaks, it's how long it's allowed to run. Studies in building risk assessment and insurance loss modeling consistently show the same pattern. The majority of severe water damage isn't caused by rare events. It's caused by common failures that go uninterrupted. Washing machine hoses, toilet supply lines, water heater connections, small components, constant pressure, no supervision. And when they fail completely. This is where it gets uncomfortable. Because from a purely mechanical standpoint, this problem isn't complex. The system already contains the signal: pressure changes, flow anomalies, immediate deviation from normal behavior. The valve doesn't need to be smart. It just needs to respond. And when it does, it doesn't prevent failure. It limits exposure, cuts duration, reduces damage, changes the outcome, which raises a different kind of question. If the physics is this clear, and the response can be this simple, why is the default system still designed to let it run? At this point, the mechanism is no longer the question. The physics is clear. The solution exists. The outcome can be changed. So the question shifts. Not can this be prevented, but why isn't it standard? And this is where the conversation moves away from plumbing and into something less visible. Because when water damage happens in a home, it doesn't end with the leak. It begins a chain: emergency plumbing, water extraction crews, industrial drying equipment running for days, material removal, mold prevention, reconstruction, each step necessary, each step costly, each step part of a system that activates only after failure has already escalated. And collectively, this isn't small. Water damage is one of the most common and most expensive types of property loss handled every year. Not because of rare disasters, but because of ordinary failures that go uninterrupted. A hose, a fitting, a valve that never closed. And once it starts, the system around it is designed to respond, not to prevent. That's where the tension begins to build. Not because prevention, by definition, is quiet. If a shutoff valve works, nothing happens. No emergency call, no restoration process, no reconstruction. The event collapses before it becomes visible. And from a system perspective, that changes everything. Because most of the economic activity tied to water damage exists after the failure, not before. This is where it gets difficult to ignore. Builders operate under cost constraints and code requirements. Their objective is to deliver a functional, compliant system, not to eliminate every low-probability risk. If a component isn't required, it competes with cost, time, and standardization. Contractors follow specification. Inspectors verify compliance. Insurance models price risk. They don't remove it entirely. Each part of the system is rational. Each decision makes sense locally. But when you step back, something else becomes visible. There is no strong incentive anywhere in that chain to reduce the scale of a failure that hasn't happened yet. Not because anyone benefits from damage directly, but because the system activates around damage, not before it. And that creates a kind of asymmetry. A $5 component can reduce a five-figure loss, but only if it's installed in advance. Once the failure begins, that option is gone, and everything that follows becomes necessary. That's not an accident, that's alignment. Not intentional, not coordinated, just consistent. Because in systems built around response, prevention is always harder to justify. It adds cost up front. It protects against something uncertain. It operates silently when it works, and silence doesn't generate urgency, so it gets deferred, or excluded, or simply never considered, until the moment it would have mattered most. And this is where the perspective starts to shift again, because now we're not just looking at a missing valve, we're looking at a system where the smallest intervention, something simple, mechanical, inexpensive, sits on the outside of what's considered standard, while the consequences of not having it are built directly into the system itself. And when you see that clearly, it becomes harder to call it an oversight. It starts to look like a pattern. So, what does this actually look like in a real home? Not a redesign, not a complex system. Just a small interruption point, placed where failure is most likely to happen, under a sink, behind a washing machine, at a toilet supply line, near a water heater connection. These are the weak points. Not because they're poorly built, but because they're constantly under pressure, often out of sight, and rarely checked. A mechanical shutoff valve sits in line with that connection. Most designs are calibrated to respond when the system behaves outside its normal range, when flow suddenly spikes, or pressure drops in a way that signals a rupture. And when that threshold is crossed, it closes. Not after minutes, not after confirmation. Immediately. That single moment changes the trajectory. Without it, water continues to move, uninterrupted, unobserved, until someone intervenes. That could be hours, it could be longer. With it, the system interrupts itself. The flow stops, the exposure shrinks, the damage stays contained. And this isn't theoretical. These valves are already used in certain applications where continuous flow is considered unacceptable. The logic is proven, the mechanism is stable, but in residential use, it's rarely treated as a default layer. It's treated as an addition, an upgrade, an option, something extra. And that framing matters more than it seems. Because the difference between standard and optional isn't technical, it's psychological. One is expected, the other is overlooked. I need to be completely honest here. This is not a universal solution. A mechanical shutoff valve won't stop every type of water damage. Slow leaks, like seepage behind walls, gradual corrosion, or small drips, may never trigger it. If the flow stays within a normal range, the system may not recognize it as a failure. And installation matters, placement matters, calibration matters. If it's installed in the wrong location, or if the failure happens outside its coverage, it won't activate. So, this isn't a guarantee, it's a layer, but in the specific type of failure that causes the most sudden, severe damage, pressurized line rupture, it can change the outcome dramatically. By now, the pattern is difficult to ignore. A small failure, common, predictable, almost routine, can escalate into massive damage, not because it's rare, but because nothing stops it. And right next to that risk, there's a solution. Simple, mechanical, quiet, a few dollars, against tens of thousands. That contrast doesn't come from complexity. It comes from timing. Stop the flow early, and the problem stays small. Let it run, and everything changes. And yet, in that early intervention, the simplest layer of protection sits just outside what we define as standard. Not rejected, not disproven, just not included. That's the shift. Because once you see it, this isn't just about plumbing anymore. It's about how systems decide what matters. Minimum standards get enforced, cost gets optimized, risk gets absorbed. But prevention? Prevention has to justify itself. And if it's quiet, if it doesn't generate urgency, if it only proves its value when nothing happens, it gets overlooked every time. This is one of those moments where it's worth pausing, not to react, but to notice. Because the question isn't just what's built into the systems around you. It's what isn't. And once you start looking for that, you don't stop seeing it. If this changed how you see standard, stay with this channel. We're just getting started. The next system looks safe until you understand what it leaves out.